Can you see my screen?
Yes, we see your screen. We hear you very well.
Okay. Good afternoon, dear colleagues. I am pleased to provide an overview on the topic work of steel fiber concrete beams under the action of repeated loads and experimental study. The aim of the study was to establish the correlation between stresses and strains in steel fiber concrete under single and repeated compression and tension, to establish the features of behavior of steel fiber concrete and steel fiber reinforced concrete bending elements under single and repeated low cycle loads. Also on slide 2, we can see the view of concrete and steel fiber concrete prisms during their testing in hydraulic press. On the next slide 3, we can see the general view of steel fiber concrete beams during their testing. The first beam, basic of each type of experimental sample, was tested under single loading until failure. The load bending capacities were as follows for the steel fiber concrete beam, equal 3 kilonewtons. For the reinforced concrete beams, equal 30 kilonewtons. And for the steel fiber reinforced concrete beams, equal 27.5 kilonewtons. The tested beams were subjected to low cycle loading with a total of 10 cycles, followed by additional loading to failure during the 11th cycle, with the exception of beam 2 BSFRC3, which was tested over 20 cycles. On the next slide 4, we can see the cubic and prismatic strengths of concrete matrix and steel fiber concrete for different series of specimens. In particular, during the compression tests of concrete and steel fiber concrete specimens, a number of distinctive features of their deformation and fracture were observed. Namely, when loaded from the natural state, the average prismatic strength of steel fiber concrete of the second series was 31.7 megapascals, exceeded the strength of the concrete matrix by 16.4%. It should be noted that the prismatic strength of steel fiber concrete calculated by formula has a good congruence with the experimental data and is 32.07 megapascal. On the slide 5, I have shown the correlation between stresses, sigma concrete, and longitudinal relative strains, epsilon concrete, under a single load to failure. The graph A and the elastic modulus versus load level of load level in concrete prisms, the graph B. On the next slide 6, we can see the correlation between stresses, sigma, steel fiber concrete, and longitudinal relative strains, epsilon, steel fiber concrete at a single load to failure, the graph A, and the elastic modulus versus load level in steel fiber concrete prisms, the graph B. The graphs in slides 5 and 6 show that the deformation of the steel fiber concrete prisms from the beginning of load until failure was similar to that of the concrete prisms. The relative longitudinal deformations developed almost identically in both cases. The difference is that when concrete reached its ultimate deformation, conventional specimens failed brittle and with concrete crumbling. In turn, steel fiber concrete prisms with 1.5% fiber content could withstand approximately 16% more load. Slide 7 shows the graphs of deformation of steel fiber concrete reinforcement, the graph A, and deflections for beam 2BSFRC1, graph B. In particular, the load-bearing capacity of the beams from the first and second series tested under single loading was 27.5 kilonewtons. The first cracks appeared at a load equal 5 kilonewton with a crack opening width of 0.02 millimeters. Compared to reinforced concrete beams, these cracks appeared more frequently and intertwined with each other. No inclined cracks were observed. The beam failed gradually without concrete spalling as a result of the reinforcement reaching its limit deformations. The deformations of the extreme fiber in the compressed zone at failure were epsilon for steel fiber concrete 308.5 to the power of -5. And the reinforcement deformations were epsilon steel fiber concrete 290 to the power of -5. The beam deflections were as follows under concentrated forces equal 1.25 centimeters and 1.37 centimeters, and it at my span 1.60 centimeters. It is worth noting that the deformations of the extreme compressed fiber of steel fiber concrete during bending before beam failure were 2.2 times greater than the limit deformation during central compression. On the next slide, 8, we can see the graphs of deformation of steel fiber concrete reinforcement, the graph A, and deflections, the graph B. In beam 2 BSFRC 2 for the first, second, third, fifth, 7th, 10th, and 11th load cycles. The performance of this beam was studied under repeated loading at a level of loading 0.75. The load-bearing capacity of the beam was 30 kilonewton. Cracks began to appear during the first cycle at a load of 5 kilonewtons, extending across the entire span of the beam and spanning vertically to a height of 2.5 to 7 centimeters, with an increase in load to 7.5 to 20 kilonewtons. New cracks formed. On the next slide, 9, we can see the deformations of compressed steel fiber concrete, tensile reinforcement, and deflections for beams third and fourth of the second series of beams. First of all, third beam was tested for low cycle fatigue at a level of loading 0.9 over 20 cycles. However, the beam withstood this loading regime and was forcibly loaded to failure. Its load-bearing capacity was 30 kilonewton. In particular, the results for fourth beam, which was tested under varying load levels, are presented in the table. On the next slide 10, we can see the changes in deformations of the extreme compressed fiber of steel fiber concrete, tensile reinforcement A, the graph A, and deflections, the graph B, in beam in 5 beam of the second series of beams. On the next slide 11, we can see the general view of the failed beams tested under single loading. And on the next slide, we can see the view of the failed beams tested under repeated low cycle loading for different beams. And the last slide, we can see conclusions. Main conclusions. First, the failure of steel fiber reinforced concrete beams occurred gradually along normal sections due to reaching ultimate deformations in the reinforcement without evident crushing or spalling in the compressed zone. Second, stabilization of compression deformations in steel fiber concrete, tensile deformations in reinforcement, and beam deflections at level of loading less 0.6 occurs during the third or fifth load-unload cycles, and at a level of loading less 0.75, stabilization occurs during the fifth to seventh cycles. Increasing the load level during certain cycles disrupts the stabilization of deformations achieved in previous cycles, leading to significant residual deformations that depend on the level of additional loading. Therefore, compared to beams made of ordinary reinforced concrete, cracks in steel fiber reinforced concrete beams appear more frequently along their length, while the crack opening widths and deflection magnitudes are significantly smaller. And the last fifth, beams made of steel fiber concrete have low strength, and therefore bending elements must be reinforced with longitudinal working bars. Thank you for your attention.